pleased to introduce Kubo. Professor Kubo, as you probably know, is a professor here in the biology department where he teaches biotechnology and microbiology and coordinates the ARC biotechnology program. So what you may not know about him, he received his BS in medical microbiology at Stanford and a PhD in biochemistry at the University of California, San Francisco. After graduate school, he did a postdoc at the Institute of Molecular Biology at the University of Oregon. And before he came to his AR, he was program director of the Biotech Project, biotechnology outreach program at the University of Arizona for high school teachers and students. So you're using all that.
That's right. I love the practice.
Here at AR, he still continues his outreach at high schools, and much of the work is done in collaboration with the North Valley Biotechnology Center on the ARC campus. He also works with Sacramento State and UC Davis in biotechnology outreach to middle and high school students. And in his spare time, he's also co-chair for American River College's accreditation. So, please, let's give him a warm welcome. Yeah.
All right, well, thank you for coming. And let's keep playing around with it.
Yeah, I think.
Try that. There we go.
Is that
Okay.
a
All right, so I know I've been asked this, so in case you want a copy of the presentation and also put some notes afterwards, I'll have them posted here. I want to use that. I always wanted to have that title, so I get to use it here. So this is where you can find it. Okay, so I'll post it afterwards. All right. So I am going to talk about astrobiology in the very small, and Professor Haig gave a good description of me, but there's a couple things I want to point out. Okay, first of all, I am not a physicist. Okay. Second of all, I'm also not an astronomer. Right? So I looked hard for this picture, by the way, so enjoy it. Okay, so of course this is the Physics Astronomy Lecture Series, so you might be wondering why I'm here. What I do know is I do know microbiology, and I also know molecular biology. So here's one of my favorite molecules. Do you recognize that? What is this? Class? Yeah, DNA, yes. All right, what about this one? Hemoglobin, protein, yes. All right, so some of the biotechnology students here know that. All the other ones, all right? So, again, this is a physics astronomy lecture, and I'm a biologist and I'm here. So why is that? So let me give you one reason. Now, do people recognize this? What was this about? Debate about, yes. So there was a debate last month, creationism versus evolution. You recognize who he is? Bill Nye, the science guy, yes, and this is Ken Ham, okay? And so during the debate, Bill Nye asked a very profound question. Are we alone in the universe? And let me give you another perspective. So if you recognize this person, who is he? Neil deGrasse Tyson, yes. Right, this astrophysicist Neil deGrasse Tyson. And he also was asked this question, are we alone in the universe? And what he said was that more than likely the first life we find would be microbial. And that would be fine too. That would transform biology. Okay, so as a microbiologist, I'm here to help us explore that question, are we alone in the universe? Something else, just to make sure we know this. So what else is Neil deGrasse Tyson known for? Especially it's going to come up pretty soon. What is it? Cosmos, yes. Cosmos is coming. It's coming in 4 days, all right? So, all right, I want to make sure I put that plug out there. So stay tuned. All right, so what we're going to look at today, first of all, we're going to look at some definitions. Right, just to get that out of the way. And then also want to explore this question. What can microbes teach us about astrobiology? And then that leads to the next question. Is there life elsewhere in the solar system? Okay, so I'm going to focus a lot of what I'm going to say kind of in our neighborhood. So, are we alone in the universe? Now what this relates to is astrobiology. It's a major topic in astrobiology. And what astrobiology addresses is to study the origins, evolution, distribution, and future of life in the universe. Okay? And so we seek to understand life, understand biology in a cosmic perspective. Now, some of the topics that are covered in astrobiology, just to give you a sense of the breadth of this field, it's actually a very interdisciplinary field. It combines lots of different areas of science, right? It's a perfect topic for or a perfect area for our division, the science division, because all of us have something to contribute to this. Right? So one of the topics is the origin and emergence of life on this planet as well as other worlds. Also, what are the limits of life? And this gets into a class of organisms called extremophiles, and I'll have something to say about that. Okay? And then, of course, what's the possibility of life elsewhere besides Earth? And finally, because of astrobiology, we have a context to try to understand about the future of life on Earth and beyond. So, in astrobiology, we have a way of thinking about, well, what would happen to Earth if this happened? Or what would happen to Earth if that happened? Okay, from a cosmic perspective. All right, so let me first, let's first start with a very simple question. What is life? Okay, now why do we care, first of all? Well, if we're going to say we're going to look for life elsewhere, like elsewhere in the universe, we have to be able to say a little bit of something about what life is already. We have to know what we're looking for. And so now how many of you had a biology class? Right? So this is often a topic somewhere in the biology class, like what is life? Okay. And so let me give you some properties about life. First of all, it grows. Okay, life grows. All right. You can see where I spend my time now. But that's okay. It also divides. Okay, so life divides. This happens to be my favorite organism in the universe as we know it, which is what? E. coli. Yes, it's E. coli. Right. That's what I spend a lot of my time studying. Okay. Some other features about life. It metabolizes. Okay, so all life metabolizes. Okay. Maybe some of you recognize who that is. Yeah, Popeye, good. Okay, we still know that. Okay, so, and also it can store instructions. So there it is, the cosmic DNA molecule, right? Life's instructions are stored in that molecule. Okay. All right, and also there is another property of life. It evolves. Okay. Right? Life evolves. Right? Just like us. See here, all right? And in fact, this idea of evolution is used as a working definition for life. So life is a self-sustained chemical system capable of undergoing Darwinian evolution. Right? So NASA scientists, this is attributed to a NASA scientist, Gerald Joyce. Okay? Right? So evolution is a very important part of this. Now, I just went over that basic list of what life is, but when you think about it, defining life is actually pretty complicated because, for example, I used one property that grows. Well, there are things that we don't think are living that actually grow. So, for example, this salt crystal, right? Okay, that grows, right? But you certainly don't think that's alive, okay? Or it divides. All right, so we work with computer files, right? They divide, they multiply. I just replicated my file onto this laptop, okay? But it's not living, right? Although I guess there is a movie now called Her, which may challenge that notion, right? So you fall in love with your operating system, right? Windows definitely not, but so it metabolizes, all right? So fire metabolizes. Right? Does anyone know where this is from? Burning Man. Oh my goodness, everyone knows what that is. Okay, Burning Man Festival, so there must be a lot of people who go there, right? And also it can store instructions. So again, right, we have ways of storing files. Okay? But certainly it's not alive. Also it evolves. So this one took a little bit of thinking, but there are non-living things that can evolve. So for example, this, right? This is an algorithm that is capable of evolution, and in this case, it's capable of creating something that looks like an image. All right, okay, all right, but that is certainly not living. okay, but it's capable of evolution. Now, although defining life is complicated, right? We kind of know it when we see it, right? So you can certainly tell which one of these is considered living and which one is non-living, okay? All right, so even though they both look similar, and they're both, at least this, hopefully this one's not on fire, this person's not on fire, but, all right, so, okay. Now, so we talked about life. That's a big issue in astrobiology. Another one is habitability, right? Habitability. So what is habitability? Okay. All right, so for example, this world could be habitable. Right? It's actually not our world. It's a depiction of another world. Okay. Habitability is the ability of a world to develop and sustain life. And this is one of the basic concepts of astrobiology. Now, what makes a world habitable? Anyone? What makes a world habitable? What do you think? Water. Okay, what else? Atmosphere, heat, sun, right? Right. So we have lots of ideas about that. Okay. Right, those are good. Those are actually really good, and we'll probably touch upon a lot of those. Here is a classic depiction, somewhat classic depiction of habitability. Okay. So let's see if we can understand this. This is what we consider. This is what's called the habitable zone. Okay. And what's depicted here on the left? Different stars, okay? And what do you notice? And this is actually our solar system, right? And you notice that the habitable zone changes as we go up and down the scale. Why is that? Yeah, stars are getting hotter, right? So as they get hotter, the habitable zone, this is where temperature comes into play, right? It's stretched out to here, okay? All right? Now, I'm going to challenge this idea a little bit as we go through this. Right? But this is a classic way that we can look at habitability. Now, there is a working definition for habitability. NASA has one, okay, which is this: habitability refers to extended regions of liquid water. So, and a lot of us are aware of this in the way that NASA is conducting business. Water seems to be very, very important. So, extended regions of liquid water, conditions favorable for the assembly of complex organic molecules, energy sources to sustain metabolism. Okay, so that's kind of their working definition of habitability. Now, this is actually important from a policy perspective because this informs, what they set up into space to look for evidence of life. Okay, so you may have a different idea about what we should be looking for, what habitability is, right? But it's this definition that shapes a lot of what they do in terms of the kind of strategies or approaches they take to looking for life beyond Earth. Right? And this actually comes from there's an astrobiology roadmap, okay, that NASA lays out, and they actually have some plans in progress now for their astrobiology roadmap. Okay, that's where this definition comes from. By the way, if you have any questions, let me know, okay? So if you have any things that you want to ask, I'll see if I can answer them. I am a biologist, though, by the way. I'm not a physicist. I'm not an astronomer. Okay. So now, mention water as an important molecule for habitability. Okay? And so, luckily our dean's here, because she's a chemist, so she can help me with this. All right. First of all, water expands when it freezes. Okay. So it actually has a solid liquid density less than 1. Now, if you're a living organism, why would this be important? Especially if you're a waterborne organism, why would this be important? Like what would happen if the solid liquid density were greater than 1? What would happen? Huh?
Fishes would die.
Yeah, ice would accumulate, right? Okay, so it would start on the bottom, sink the bottom, and then year by year, what would happen to the ice? It would build up, right? Okay, so that would not be very good if you're a fish. Okay, and we'll see where this comes into play, where this becomes important in one of the examples that I'll bring up. Also, water absorbs heat well. Okay, high specific heat. So what does that mean for the temperature if you're like a watery body? It doesn't rise quickly, right? It has that stability. Okay, all right. So In fact, there are these visions, these alien planet visions of like water worlds, right? Those water where the whole body is virtually covered with water, but that's good for habitability because you may be able to support life in that way. Water is also an excellent solvent. Okay, you can dissolve things in water, lots of different things in water, and that's good for dispersing out chemicals, different molecules that might be important for life. Okay? And along those lines, water takes part in many chemical reactions. Okay? So now in the laboratory, right? So I teach biotechnology, and we kind of have a working relationship with water. We just use it to make things work, okay, without really understanding why it works or how it does what it does, but it works. Okay? But this is going back to why water is so important, right? Okay? And so water is a very important molecule for life as we know it right now. And also, water is abundant, not only on Earth, okay, but also in the universe. All right? So what is water made of? Let me ask a basic question. What is water made of? Hydrogen and oxygen. Now, if you think about it, how abundant are those two elements? Yeah, hydrogen is extremely abundant. Okay, so this is a very easy to make molecule from from a universe perspective because we have a lot of those materials around. Okay. All right. So now let's take a look at Earth. Right. So one of my key themes to try to justify why I'm here is that we can use biology, microbiology especially, to understand astronomy. Okay, and so what we're going to look at are some organisms here on Earth, okay, which can help us understand how life might be able to be sustained and developed beyond Earth. All right, so one is to think about temperature. That was one of the things that was brought up about habitability, was temperature. Okay? And one of the issues in astrobiology is what is the limit of life? So that is, how hot can things be, right, but still sustain life? Now, this is on Earth. Is that what this is? Where this is? Yeah, sea vent, right? This is one of those black smokers, right? Deep sea vent. And how hot is that? It's very hot, yes, very hot. Okay, so in fact, it was a great surprise that scientists were able to actually find thriving microbes in this kind of environment. So here's one. This is Paracoccus furiosus. Okay, all right. Just for the name, you know that it likes to be hot. Okay, all right. So its optimal growth is 100 degrees Celsius. Now, how hot is that? Boiling point of water. Yes. Okay. That is where it likes to. That's where it likes to grow best. Okay. We don't grow very well at that temperature, by the way. All right. But this organism does, and it has a range from 70 to 103 degrees Celsius. Okay. All right. Let me give you another one. All right. Geogama barosi. All right. It has an optimal growth of 115 degrees Celsius. Okay. So how does that compare to boiling point of water? It's even more. Yes. Okay. All right. It has a range of 85 to 121 degrees Celsius. Now this brings up a little science story. Okay, so now some of you, how many of you taken microbiology? A few of us. How many of you worked with microbes like bacteria or like E. coli? All right, some of us. Okay, so some of you may know. All right, if you had like E. coli and you wanted to like kill it, right? And you're in a class, how do you do that? Heat it up, right? Does anyone know what you actually use to heat it up?
Water.
Yeah, that's true. But so, like, if you're in a hospital, and you want to, let's say, sterilize something. Yeah, what do we call that? High pressure steam. What do we call that device? Autoclave. Yes, an autoclave. Good. I know we get there sooner or later. Right. So the reason why I bring that up is this group of scientists who are looking at this organism thought, well, heck, let's see what happens to this after autoclaves. After autoclave it. So they actually stuck through an autoclave. Now I worked with E. coli for years, right? If I put E. coli in an autoclave, right, and I took it out afterwards, what would happen to my E. coli? Yeah, it'd be dead, right? I would be without my E. coli, right? Which is It's not going to happen, okay? So if it's, however, this organism, they pulled it out and it is thriving. It's thriving after being subjected to an autoclave, okay? All right, so think about that. Think about that, all right? And this is here on Earth. Now, apparently the current record holder is this one, the Thanopyrus candeleri. This is what it looks like. Okay. Now, it has an optimal growth a little bit lower than the other ones, 90 degrees Celsius. But, right, it can sustain, it can live at the hottest temperature. Now, we're talking about living as in terms of being able to grow and divide, okay? What scientists do know is that they can raise the temperature and it will still be alive. They can't kill it. Right? It will still be alive. And when they lower the temperature, it will start to divide again. Okay? All right? So these are this is what we call extremophiles. Yes?
Just a quick question. For the first time, I noticed that the optimal growth is very near its high end and further from its low end, but not so for the last one.
Yeah, that's an interesting question. I'm not sure if they know the answer to that. One of the ways of trying to address it, so they've actually recently determined the genetic sequence for all these organisms. I think this is the last one that they've determined. And so they're hoping from the genetic sequence to try to figure out what is special about the proteins that encodes. So it may encode certain proteins that can tolerate a wider range, have more flexibility in how they operate. Because that's one possibility. But that's a good question. It's not really known. Right, so there are certainly organisms, even here on Earth, that can tolerate very high temperatures, okay? Another way to challenge organisms here on Earth is cold, right? And we have a way to look at that, which is here, Vostok Station, Antarctica. This has been in the news, by the way, because there's been a lot of interesting scientific work coming from this area, okay? And what's special about Lake Vostok is that there is a lake, but it's way deep down this whole thick sheet of ice. Okay, all right. So this goes back to why solid ice is less dense than water, liquid water. Okay, because you can have this liquid body of water protected beneath that ice. And so the question is there anything living down there? Right? How cold is it down there? Probably pretty cold. Okay, it's actually pretty cold. Right? I think they measured it at minus 13 degrees Celsius. Okay, so again, the freezing point of water is 0. Right? So this is below freezing. Okay, all right. Actually, does anybody know why it's not frozen? It's below the freezing point of water. That's right, pressure. And what else is down there? What else is in that water? Salty. It's very salty. It's actually about 5 times saltier than the ocean. Okay? Right, and so the way they do this, so they actually don't send someone down there with a cup, okay? So what they do is they take these ice cores. Okay? Now, ice cores is used in a lot of different fields of research. Okay? So we're actually using it to investigate climate change, for example. Okay? Because think about this, we're actually looking back in time. Right? So we're looking at a body of water that's been there for a long, long, long time, okay? And it's been sealed off from the rest of the world by that ice. So it gives us a chance to look at ancient history, right? So you can look back in the past and understand different processes that might have occurred on Earth, which is why climate change scientists are interested in studying this area. And what you can do is you can see, is there any organisms that you can find once you get down into this body of water. And in fact, they can find microorganisms. Right? So here's an example of microorganisms that they actually grew from a sample that they were able to collect deep down in that lake. Okay. All right. I just want to show this. I just want to show one data-heavy slide here, because I'm a biologist, and this is the only real biology slide that I have, okay? But the key point here is that they've been able to determine what kinds of organisms exist in that lake. This is Lake Vostok. So here's the ice layer, Here's their little drill, right, to show you how far it is. That's pretty far down. And then they've taken two samples. Looks like they've taken one from here and one from here. And you can't read a lot of this, but what they found is they were able to identify over 1,500 different types of organisms in one sample. Right? And this one's a smaller one where they have 80 different types of organisms. Okay? All right? Now, those are the ones they can identify. There's over 3,300 that they can't identify. Right? So there's actually a lot more organisms that they can't identify versus ones that they can identify based on what we know what exists elsewhere. Okay? Right? Does anyone know how they were able to identify them? What do they do? Gene sequencing, yes, right? It's DNA. It's actually DNA barcoding. Right? For some of the students here will know what that is, because we're actually doing that with fish. Okay? All right? So this is all based on DNA barcoding, just looking at DNA from these isolate the DNA from these organisms. You don't have to grow anything. You just isolate the DNA, and then you sequence it and try to figure out what it is. Okay? All right? Now, some of you up close may notice there's some interesting listings here. For example, they list fungi. They even list fish. Right? That's tantalizing, right? So it still remains to be determined if there's actually fish swimming around there, which would be amazing. Okay? Right? They haven't been able to eliminate that, and or whether it's just like fish from like 1 million years ago, right? That's hanging out, that's just kind of decaying down there. What they do know, though, just to tantalize you, so maybe one of you will actually like dive down that hole and tell us what the actual answer is. What they do find is that so all these fish have, some of you may know, they have parasites, right? They have other organisms living on them, right? They can find those organisms. Right? They can actually find those organisms. And so these are mostly microbes. And so the idea is, well, if these microbes have to depend on living fish in order to live, and we're finding these living organisms, right? They're able to isolate some of them. Well, maybe there's actually a living fish down there somehow. Okay? It kind of defies all their logic, but maybe there's something down there. Okay? All right? Maybe there's a deep sea monster down there. Okay? Okay, so just one other challenge. This actually comes up when we talk about space. Right? One of the things that's keeping us from jumping on a rocket ship and going to Mars is actually radiation. Okay? Because we actually can't tolerate a lot of radiation. Our lethal dose is 500 to 1,000 rads. Okay? However, there are bacteria. So Dinococcus radiodurans, also known as Conan the bacterium. Okay. This is what it looks like, all right? And you can give it 1.5 million rads. 1.5 million rads, and it thrives on that. Okay, it thrives on that. Okay? Okay? Scientists are beginning to figure out, or begin to understand how this happens, right? You think that, with that kind of dosage, you just obliterate it. Yes, yes. So apparently this bacteria has many copies of its DNA, has many copies of instructions, has backup files, right? And so, now what does radiation do to DNA? It just breaks it up, right? But this organism, because it has backup files, it can stitch back together its genetic instructions, right? And the thought is, because radiation is a problem for us, is that because we really understand what biochemical processes are involved with that, what molecular processes are involved with that. Perhaps it might be possible one day to do the same with our DNA. So if you get zapped by that Fukushima radiation that's slowly making its way over here, okay, there might be a way to repair your DNA. All right, so habitability, right? We've been talking about habitability, and as I described, some of the organisms that we have here on Earth, right, without having to jump on a rocket ship, but here on Earth, right, challenge this definition because we can actually expand, right, what could be habitable based on this, okay? All right, so I want you to think about that because we're going to look at that question a little more, right? And one of the big questions is, does life exist elsewhere in the solar system? So not just here on Earth, but does it exist elsewhere? The answer to that question would be very profound, right? It would just blow our minds, right? If we realize that we're not the only ones here in the solar system, right? But life just doesn't exist here on Earth, but elsewhere. Okay. So I'm just going to focus on a few worlds here, and just to make sure we know what worlds we're talking about. So hopefully, what's this one? All right, Earth. Yes, good. Okay. And let me ask you this: Does the Earth orbit the Sun, or does the Sun orbit the Earth? Okay. So yeah. So there was actually a National Science Foundation survey that was done, and the results of that question were very discouraging for all the science teachers. Okay. What about this one? Mars. Good. Okay. Now this was a little harder one. Europa. Good. Wow. Smart group. Okay. So that's Europa. So I'm going to focus on these two. Okay. So one question, and a lot of you are aware of this. One question is, because it's been in the news, is is Mars habitable? Okay. Is Mars habitable? Now we do have some help. What's this? Which one? Curiosity. Yes, it's Curiosity, right? So Curiosity is alive and well, exploring Mars, and it's made some profound findings about, or some exciting findings about habitability. Okay? So here's one of the early ones. There's a picture of Mars, a picture of Earth. Now, if you were to see this, as you look at the Earth, where would you think this was?
Riverbed.
It's a riverbed, yes, right? So see how smooth the rocks are, right? This is actually a riverbed. And here's a comparable picture of Mars, right? It looks just like a riverbed, right? Riverbed indicates the presence of what? Water, right? So we don't think there's water running through right now, but maybe a long time ago there was. In fact, one vision of what this area looks like, so this is where Curiosity is. It's in this, of course it's dry now, but it's in this area called Gale Crater. Okay, and the vision of history is that it was actually a lake. Okay, it was actually a lake. In fact, this was announced in December, right? So where they reported, this is Jim Bell from ASU. It was at the AGU meeting in December, American Geophysical Union meeting. It said that 3 results from the Spirit Opportunity, which were the other 2 rovers that were sent a while ago. One of them is still running, by the way. Okay. Point to very acidic water, but what we're seeing in Gale Crater is evidence of fresh water, very neutral, very drinkable. Right? So yes.
Haven't they found like photos of water coming from underneath the surface?
Yeah. So some very intriguing photos. They can see seepage. Okay, and so there are those photos too, and it seems to be seasonal as well. So, yeah, very, very intriguing, at least photos that they've been able to get from Mars. Okay? And so the idea is that, if this would have to be a long time ago, maybe hundreds of millions of years ago, you could get a cup of Martian water and drink it, right? And they also seems pretty obvious to them that the kind of microbes that we have here on Earth could very well live on Mars under these conditions. So we're looking at sort of Mars history here. This is Mars probably about maybe hundreds of millions of years ago, billion years ago. Okay. Europa. So Europa has water. At least we think it has water. Okay. It turns out that there is not water on the surface, although I'm going to challenge that a little bit, but that there's water beneath the surface. So there is this. You might imagine, Europa is found where? It's orbiting what? Jupiter, yes. So it's actually one of Jupiter's moons, right? And Jupiter is very, very cold, I imagine. Okay, all right, because it's far away, out of that classic habitability zone, right? However, Europa has an ocean, but it's beneath the surface. Okay, all right. So there's actually the thinking now is that there's actually liquid water underneath the surface of Europa. Okay. So apparently Europa is under a lot of gravitational pressure, and there's some kind of physics pressure which I barely understand, which keeps it warm.
Tidal heating.
Yes. Okay. So All right, somebody actually know the scientific term for that. I would have formed that part of the National Science Foundation survey. All right, so now, one of the intriguing ideas, and this has actually very intriguing space implications, is there water on the surface? Right? There's this deep subsurface ocean, but is there water on the surface? One finding is that there actually might be leakage to the surface, and this is from spectral data. Okay? They found some indication that there actually be water seeping to the surface. Right? So the idea is that maybe there's little springs of water that are trickling to the surface. Okay? In fact, last December, there was a report that there might even be geysers. All right? This was observations from the Hubble Space Telescope. Okay? So there actually might be geysers on Europa. Now there's some big space implications for the space exploration implications from this. Because before these findings, which came out last year, the thought was, well, there's this ocean that's way deep beneath the surface. So we have to like bring a big drill to figure out a way to get down beneath the surface. Okay? But now it might be a lot easier. We can just simply send something to scoop up the water, right? Send something with a cup, right? And then like you can sample that geyser or dip into that spring, right? And then you have your water that you can examine, right? So it's very, very, very provocative, okay, in terms of what you might be able to do to look for the evidence of life. Now, I've mentioned places that you have to go far away, like Mars or Europa, okay? But there is a shortcut, okay? There's actually pieces of space bodies that are coming to Earth, and those are meteorites, right? Okay, so actually, here's a meteorite. Where are these scientists right now? Somewhere cold, yes. Okay, it's not Europa, by the way. Where on Earth are they? They're in Antarctica. Okay, so why would they want to be in Antarctica looking for meteorites? Yeah, okay, so how easy is it to find that meteorite? It stands out, right? So remember, scientists were once students. You want to do things the easy way, right? If you're looking for something black, everything around is white, you're going to be able to find that meteorite, okay? All right, so, and it turns out they're finding meteorites that have come from Mars. All right, so, you know, we sent Curiosity to Mars, but you can actually get pieces of Mars coming to Earth. This actually just came out, so it seems like a lot of this stuff is just coming out. This was announced last week. There is a meteorite that's been studied for actually about a decade, and they determined that it was formed about 1.3 billion years ago. Right? So we're looking at a piece of Mars from ancient history, 1.3 billion years ago. What they find is that there's water evidence in the meteorite. Okay, so based on the structure of that meteorite, within the meteorite, right, they're finding that this is indications of water. This is why this particular area of science is so interdisciplinary, right? If we had like Earth scientists in this room, right, they would obviously conclude that shows evidence of water, right? To me, it just looks like squiggly lines and, you know, fissures and all this fun stuff, okay? Also, they found that there's carbon-rich structures, and those carbon-rich structures, based on the chemistry, indicates that they could have formed by biological processes. So they find these types of structures. Okay? Now there's a lot of caution about this, and the scientists who published this raised that because I remember this from Arizona, which is kind of like space central in the United States in a way. There's a lot of astronomy going on there. There was an announcement about in the 90s where they found these structures that look like bacteria, little bacteria. And it was such hoopla because it came from Mars. We thought, oh, these are Martian microbes, right? But it turns out that those could have formed very easily from non-biological processes. So it still remains to be determined what processes formed these, but it's very intriguing. Okay? And again, this is another indication that there's water, that Mars had water. All right, now I mentioned that astrobiology gives us a way to look at the future. So first of all, one question is how are we going to explore just these two worlds? There's others, but how are we going to explore these two worlds? One obvious way, okay, which a lot of space scientists are thinking about, but the government is not yet ready to fund, I guess, is a Mars sample return. That would be very obvious, right, as a next step. We find evidence of water on Mars, we find these habitable areas. Why not just like get a shovel, dig up a sample, and look, there could be fossils in there, right? There could be fossils, okay? Right, so one idea is to actually bring back a sample, okay? There's also thoughts about sending a probe to Europa. So one idea is the Europa Clipper, okay, to send, and so NASA JPL has this idea where they'll send a spacecraft to Europa to try to explore more for evidence of life. Okay. Again, these are just two ideas in the works. Whether they get funded or not remains to be determined. All right? Now I want to look back at this idea of habitability. So we've been focusing here on, that yellow star, the sun. All right, what about these other stars? Okay, could they have habitable planets? Right, and so there is a spacecraft called Kepler. Now, what is Kepler famous for? Planet hunting, yes. Okay. All right, so here's Kepler, and its mission was to look for planets not around our solar system, but around other stars. And in fact, right, you might imagine there might be a lot of stars that have these planetary systems. And what they're finding is that, and this again came up very recently, right? They are finding these are planets that they found orbiting other stars, and apparently this year has been a big boom for exoplanets. Right? So looking at the Kepler data, they find lots of exoplanets, more than ever found before. Right? And they're finding planets, not only planets, but also planets that are in the habitable zone. Okay? Right? So we may not be unique in being, the only planet around that has life. Right? Right, so that's something that's going to be for another future journey to find out. Now, there is another aspect of the future of astrobiology, and for this, we're going to look at the past in a bit. One question, and it's actually a very important question for us, because we're here on Earth, is will Earth's habitability change? Okay, will the habitability of our planet change? That's not an unusual question to ask, because if we look at history, Earth's history, there's evidence of mass extinctions in our past. And in fact, so what this is a graph showing millions of years ago, and it shows extinction rate. And you can see these big ellipses right here, right? This shows the rate of extinction. There's been periods of time where there's been massive extinctions. Okay, so we're looking at millions of families per million years. Right? So that's one way of measuring the extinction rate. And one that we have a little more information about is this one, the most recent one, which was about 75 million years ago. Does anyone know what caused this one? Yeah, meteorite. We think this big meteorite crashed in the Earth, right, and caused global catastrophe. Okay, right? Now, the reason why I bring this up is, again, will Earth's habitability change? There's thought that we're actually going through another extinction. Right? So this would be the sixth mass extinction. Okay, and so this is the red indicates the species that are projected to be lost. So it's a sizable percentage of species that currently exist on Earth. In fact, there's a book that just came out about a month ago by Elizabeth Colbert called The Sixth Extinction, where she explores this idea in more detail. Okay? All right, so again, astrobiology can provide a context for trying to understand habitability and how it changes. Now, just to bring up this point, what's different about this mass extinction versus the other ones? What's causing this one? Humans, right. So we think this one's human caused, okay? All right? So we're actually causing what might be our own demise. Okay? So, just to close, right? We know that defining life and habitability is complicated, but what we have learned expands life's limits, right? So we can look in places that we wouldn't have thought of before because we can find examples of life here on Earth in extreme environments, right? Somewhat extreme environments, and we can look to other planets or other worlds and find those similar environments which open up the possibility of life. Right? So extremophiles on Earth have greatly expanded what we can look for in the solar system and beyond. Right? And also, astrobiology, just to bring it back home, it provides a context for understanding our history as well as what our future will be. Okay, so I am going to stop there. Thank you for your attention.
So, we'll take some questions. I'm just going to comment before you leave. There is a flyer for the rest of our series and some cookies if you want. Get a cookie and grab a flyer. Do we have some questions for Professor? Please.
I have a couple.
Yeah.
So you're talking about sampling and bringing back from Mars.
Yeah.
And I've heard that the biggest concern about that is contamination.
Yes.
And it seems like the really easy counter-argument to that would be that, we've already been treating meteorites, back and forth.
Mm-hmm.
What really is the danger of contamination at that point?
Yeah, so right in meteor is pretty harsh, so probably that has something to do with it. And we do know that microbes, even microbes on Earth, can survive for time and space. So one concern, especially with the current spacecraft being sent over to Mars, is that we're actually inadvertently bringing things from Earth to Mars. So they actually turn out to be, even microbes here on Earth turn out to be pretty hardy. And so there is that issue of contamination. So what we might be finding on Mars may actually be something that already existed, that we actually just brought from Earth to Mars. There is a way to address that, though. Right? So this is one of the crazy ideas that have come out of I guess it comes out of biotechnology, to be honest. So there is a scientist that's named Craig Venter. Does anyone know who he is?
Yeah.
What do you do? Genome Project, right? He is like the sequencing guru. Okay? He just started a company, by the way, that will extend your life, right, just for information, based on DNA. Okay? But more relevant to what this discussion is, he is also exploring life on Mars. Right? He's making the grand wager that life on Mars will be DNA-based. Right? So think about that. Life on Mars will be DNA-based. And so his idea is that if there is life on Mars, we can just simply take a sample of, let's say, Martian soil. We'll isolate the DNA, we'll sequence it, and we'll digitally transmit that sequence to Earth. Okay? All right. And those of us who know how DNA sequencing has gone, right? That's not an impossible idea, at least in technology. Whether there's actually DNA on Mars right now is another issue, but that's his grand wager, and that would be a way to get around that contamination issue, right? But you have to know exactly what you're looking for and how to transmit that information, not by sending microbes back, but by actually sending the information back. Okay, so that's another possible way.
Would you be willing to share the URL for your presentation?
Yeah, it is. It's bit.ly and then it's Astrokubo. Okay. So I will have my slides up there as well as my notes up there.
Turn on the link.
All right, Astrokubo. Isn't that a great name? I've always wanted that name. I can have it. Yes. Any other? Yes.
So you said that you was making the assumption that life would be DNA-based,
Yes.
but by the description of what you gave as qualities of life, it's conceivable that, I think it would be conceivable that life wouldn't necessarily be carbon-based or DNA-based. Is there any big brains out there that are grinding away trying to figure out what we might be looking for, if we're looking for some other evidence that would not be within the blinders that we have of carbon?
Yeah, there are people thinking about that. So to give you one nearby, so this doesn't get around the carbon base, but it gets around the basic assumption that we're all operating on, which is it's water based. Another possible world for life is Titan. Okay? In fact, they found oceans on Titan, but they're not oceans of water; they're oceans of ethane and methane. Okay? And so one idea is that there might be organisms that metabolize hydrocarbons, right? And there was actually a model proposed for how that might happen. Like you'd see declines in certain chemicals like hydrogen and acetylene. Okay, all right. I'm looking to the chemist here to make sure I'm actually mentioning something that has CNH in it. Okay, all right. So and that there would be a decline in a certain way, and lo and behold, they actually found that. Right. So this came out about 3 years ago now. Right. That oh my gosh, there's life on Titan, right? That was a big headline news. But then the scientists thought, well, wait a minute, you know, there could be some other non-biological processes that do that. But that's an example of non-water-based life. As far as non-carbon, so what makes carbon so cool for life is that it operates within the habitable temperatures. But there are scientists who speculate that maybe there is life that can operate at very, very high temperatures, so they have a very different chemistry. Okay? But you have to be able to break and form bonds. Carbon can do that very easily at this temperature, but maybe, and they're even envisioning like stars, something at star-like temperatures, where you can have very hot chemistry going on, and there might be possibilities for life. That's going more extreme. Okay. Yeah. They don't have the, I think it's because they don't have the right so one of the possibilities is silicon. Right, so I think from Venus they haven't apparently with the vision with the scenario I just raised, Venus is not hot enough for that. You need even higher temperatures than that. Okay. Yes.
I know there's an astrobiology course at Sac City. Is there any chance that we'll be getting in here later on?
Alfonso, where are you?
There is an astrobiology course.
Huh?
Yeah, there is. Yeah, I remember Alfonso teaches it. Is it just an intro course, or is that the only one that's available?
We only have one astrobiology course. I think it's the Astro 330. I think it's the Astro 330.
Any other questions? So I will put in a plug next week. The universe in your backyard. There is someone coming here at noon next Wednesday to talk about astrophotography if you're interested.
Just after, he's a world-renowned astrophotographer. He's big time, and he brings some beautiful pictures.
Yes. So let's go ahead and thank Professor Kubo